such a small audience, I'm inclined to ask you whether you have any expertise in neural networks or digital audio. A bit of both, or a bit more neural networks, I would imagine. Yeah, exactly. So this paper is something that I invented, I believe. I haven't really read all the possible papers, but there is a certain cross-disciplinary approach here which might be of wider relevance as well. My expertise is digital audio, and I have studied and used neural networks in the past. And most recently, our research boss, he asked me to try something with Izhikevich neurons. I don't know if you've heard of these. They have a special kind of triggering function. And he asked me to do something with sound. I mean, it's an unconventional computing group we have in Bristol. And normally if they want to sonify something, there's something with sound, I come in. And I was fiddling with these specific Izhikevich, probably Russian, I think, guy who came up with these neurons. And I realized that, well, they don't really do the thing that I need them to do in order to produce a variety of sounds. So I actually went to think of an actual network that would be perfectly suitable for digital audio. So as a matter of background, digital audio has been synthesized with neural networks. Initially, what we've been doing is controlling parameters, right? Neural networks are amazing black box blind machines. So as long as you set up the input-output stages, you do your training, they will actually do a variety of interesting things in terms of sound. Now, my interest went more into directly synthesizing the sound, meaning the waveform, right? So the waveform of a sound is sampled at about 44,000 hertz. So that's the amount of samples per second we have. So I was looking for solutions to actually clock the network at this rate and actually spit out a waveform that would produce interesting sounds. And this has also been done. It's more specifically with recurrent neural networks. And escapes me now, but there are certain networks which actually have delay times per input stage. So what you would get is that the first input has 0 delay, and then 1 sample delay, 2 sample delays, 3 sample delays. Essentially a kind of finite impulse response structure. Now this was already getting into where I was wanting to be, but the most important thing for me was to escape from the shackles of having the black box, the neural network. So I was actually wanting to develop something which will allow me to directly translate, and that's the key thing here, directly translate an audio signal processing scheme into a neural network, rather than doing the usual thing, which is, okay, these are my inputs, these are my outputs, so this smart thing will do its thing. Instead, I wanted to make it more transparent, so I actually expanded the basic structure in order to allow me to do this. Now, just briefly, what do digital audio processes require in terms of computation? It's not a lot, right? So addition, multiplication, and delay, pretty much it. There is a bit of a discussion to be had around division, whether it's necessary or not, but I tend to think that that I can approximate, the neural networks can approximate the hyperbolic transfer fairly accurately within a limited band. And normally with audio we don't want band unlimited things going on. So actually it might even serve the audio the fact that there is no division there, because it's a highly nonlinear thing in the scheme of things. So yeah, so that's what I've done. So essentially the structure of the network is what is called a fully connected graph. So what I have is n cells and n square links. Right? So every cell or a neuron, I tend to call them cells, I'm not sure why, and links are kind of synapses, but I guess these terms are interchangeable. So for every cell, you would have a link to all the other cells and itself. So I kind of have a small network here with 3 cells and then 3 square, which is 9 links. And then you see that actually there is here, this is the 0 cell, and then on top is the 0 link. So you see it's a kind of a two-way link. So a cell has a link not only to the other cells, but also to itself. And then actually each cell will be related to the input and to the output stages as well. And before I go on, I have to highlight that this is a largely redundant thing. I mean, there are a few things that I'm looking forward to discover in terms of optimizing it, but at this stage, the main thing, as I said, is to have a direct translation between audio and neural network processing. So this is the structure, cells and links, and here is a cell. So what a cell does, which is different from normal neural networks, is that it has a product, right? So I haven't really identified any neural networks that actually do a multiplication inside the neuron. Normally it is just summing things, but because of the digital audio requirements, we actually have multiplying nodes fairly frequently, and we need them. So instead of trying to fudge it with a general network, I explicitly put in a multiplier. And then all there is to it is that there are essentially two nodes. We have one multiplier and one adder. So these receive all the other cell outputs, right? So every cell is connected with every other cell. And then essentially there are two multipliers inside. One is the product and the other one is the sum, in order to balance the amount of product and the sum. And there is an input multiplier and an output multiplier. So obviously you can set these to 0 and then it will act as a cell somewhere in the layers, unseen to the input and output, or indeed you can have every cell have see all the inputs and outputs. So that's the insides of a cell, and then the insides of a link look a bit like this. So a link is a simpler thing, obviously just a single input and a single output. We have a delay in there, which is crucial, multiplier and adder. This delay is variable length. So one of the things which is crucial in designing this highly redundant neural network is that it should allow us to produce waveguides. So waveguides in sound synthesis are essentially models of single-dimensional objects, and we use them for physical modeling of sound sources, typically a string, a bore of an instrument, which is essentially a waveguide, meaning that it's just a feedback loop around a delay time, and this delay time actually specifies the resonant frequency of the system. So rather than relying on this resonance arising from the network, we explicitly have it available to actually set a delay time to however many samples to give us an audible frequency, right? Because if we're clocking this at 44K, then an audible frequency of 200 Hertz is actually a really low frequency signal at that sample rate. So rather than relying on the network, we can explicitly do it here. And with doing that, well, I can just add a waveguide, I can add a bore of the instrument just with another cell. That's the crucial thing. So actually what this network does is combines the ability to produce very long delays and zero delays. But that will be one of the crucial things, and the reason is that for waveguides, in digital audio we need long delays, and for polynomials we need zero delays. We need a lot of multiplications firing at the same time, so zero delays. So those are the two things which I achieved by producing this model. Now, before I go to any examples, I'll show you briefly the algorithm that actually calculates the cells, right? So if I go back to this picture, I can briefly explain you the main issue here. So you understand that each one of these links can have a zero delay, right? And you see the density of interconnections, so it can become a problem. You cannot run this network with too many zero delays. So what I have as a matter of calculating this algorithm, this network, is a flexible algorithm which essentially pulls the data from where it's supposed to come from, and it kind of recursively does this. So it kind of builds up a stack of things, stack of calls, and then starts from the end, because it might actually try to call its own value. And that's essentially this little trick. So if I start computing from cell 0, it will actually query all the input stages, and then from those cells it will query their inputs, and if at any point it actually goes around in the loop and asks itself for the value, then it just spits out the previous value. So it kind of injects a single sample delay when necessary. But for the rest of it, it can actually run like that. It's a matter of fact that in certain situations, starting from a different cell would actually yield a different computation sequence. But that's not a real issue, because in this context, we are just about making funny sounds, really. So that's the algorithm that computes it. And then comes the main example in this preliminary study. Obviously, it hasn't gone too far yet, which is a snare drum synthesis. Okay, so in neural networks in this field, we have had a lot of interesting, acoustically relevant synthetic sounds synthesized. But again, it was always a black box. It was always, we had the input stages, output stages, and so on. But what I've managed to do is actually make a translation from a simple snare drum synthesis algorithm into this type of network. So a few things. I'll just briefly mention the bipod. This is our kind of Swiss knife in audio. We use it for all sorts of filtering. There is a translation in the paper, if you're interested, from this bipod scheme with 2 delays, certain amount of multipliers into the DAN scheme. But what I'm actually, and here are the parameters for that, so you can actually see how it pans out. But the nice thing about snare synthesis is that I've managed to do this with 5 cells. Right? So no matter the fact that the neural network is highly redundant, the fact is that I can take a complex audio processing scheme and directly translate it into the network. And obviously, I didn't talk much about that, but it kind of is an obvious thing, that then you have all the tool set of neural networks to work with it, right? Because it's a scheme which conforms to that type of algorithm. So in order to synthesize a snare drum, what I have here first is a logistic noise oscillator. So this is just a logistic map with certain parameters, which gives me kind of whitish noise, audible noise. And this scheme, this is a typical kind of DSP scheme that we tend to look at in signal processing for audio. You see what it has. It has one multiplier node, which actually feeds from multiple inputs. It has few fixed parameters and a kind of a feedback loop and a delay. So actually all of these things, as you've seen, can easily be translated into this neural network. So all there is to it actually is this one noise oscillator. This actually takes 3 cells to compute this, to translate this type of noise oscillator into the DAN network. And then in order to make it a snare drum, I need another 1 cell, which acts as a decay. Right? So if you have 1 cell and it has its personal feedback loop, right? It has its own link, and you set the feedback, you set the gain factor to 0.9 and you set the delay to 1, then you get a neat little exponential decay coming out of a single cell, right? So I can create an envelope, we call this an envelope in audio, from a single cell. I have a noise generator from 3 cells, and then the only thing is to multiply the 2, right? So if I multiply the noise with my envelope, then I get the kind of snare sound coming out of it. So that's this preliminary study. I hope to find people who are experts in neural networks and actually can help me out with certain things here. There's a very interesting project going on now called Mimic Project. The website is mimicproject.com. I can advise you to have a look if you're interested. It is actually for the first time that we have in audio, digital audio community, a very transparent and kind of handy, easy to use framework to build our own little networks. Or actually use the traditional networks for our own little purposes. So I'm hoping, the main guy behind the project is Thor Magnusson, a guy I know years back, and he's interested to kind of squeeze this in, and we'll see what happens. But just as a matter of smallish evaluation, I can't quite evaluate this idea at this stage. I've had some feedback from experts, which was good, but most of it was not good, so we'll see how that pans out. But what I've done here as a conclusion to the paper is I've started randomizing the network. So I didn't start training it yet. I'm kind of waiting for the Mimic project to help me with this side of things. But what I've done is I've just randomized this, and with the smallest amount of randomization, it's a 1,000th of variation, randomness going into all these parameters. What I get is a large arch variety of different things. Actually, half of those randomized snare sounds blow up, right? Because there is a lot of feedback potential in the system, and easily just goes out of computational limits. But the other half, some of these things were quite interesting. So I have two examples here. This is one of the spectrograms, and what you see here is a kind of peculiar noise character, which then gets into a more uniform noise character, and it also seems to have this kind of spectral envelope going, right? And that's an interesting thing, because actually, in order for me to produce this with generic digital audio tools, I would actually have to have a filter in there, I would actually have to have a low frequency modulator for that shape, and I would actually have to have some handle on how this noise actually transforms itself. But this basic 5-cell snare sound network does this with the smallest of randomization. So what I do expect is a horribly unstable kind of space of possibilities, and hopefully some luck in taming it. And then just another one example, this is also the exact same network with very little randomization of the values. And what you have here again is a kind of a specific noise spectrum to start with some resonance in the top frequency. You see the bold line there. And then suddenly all this noise goes much quieter, it pretty much stops, and then there are certain oscillations that carry on. So it's just there to show you how, with very small variation of this network, the kind of variety of things that arise is huge. And that's something I hope to see develop, so we'll see how it goes. I think that is pretty much it. So if there's any questions, I'm happy to take those.
Yes.
I'm not expert, but if I understood correctly, there is some method how to transform this device, which is usually used in audio applications, into your network.
Yes.
And how did you, this is like a universal algorithm, or did you find this by some?
Currently I do it by hand. It's a bit of a puzzle. Yeah. I have one scheme. I know how my network looks like, and then I'm like, okay, what is this node? What is that node? I do it by hand, but technically it is possible to translate it automatically.
If this translation is somehow, if you have some other device, you can use the same rules with this translation, or you have to think about this. And it is in this paper, yes?
Well, there is no real detail on how I translate. I can show you this example. This is the bipod.
Because this is interesting. This means that it's like more deterministic approach. That you have some device, you can deterministically make something. Why do you want to make from this a neural network?
Because then I want the whole set of neural computing to be able to transform it, to adjust it. I mean, in a sense, it's a kind of an informed neural network building. So, for example, if I have, well, this rack right there, right? So there's probably a compressor in there, or some kind of denoiser, something like this. So what I can do, instead of taking a completely blind network and say, here's your inputs, here's your outputs, now learn that, what I can do is I can take a sketch of a denoiser, because I already know from my DSP background how the denoiser actually works. So I can produce a much smaller, more compact scheme that does basic denoising, and then on top of that, I can train it to be more accurate or to do certain things that it otherwise wouldn't. And actually my hope is that what you've seen here is a really complex behavior of a very simple network. What my hope is that typically a compressor, which in DSP we would build from maybe 10 multiplications, 5 additions. My hope is that actually with this network we can come up with a smaller, we can optimize the network, and my real kind of far-fetched hope is that it can even teach us about a trick that we might not be aware of. Because, I mean, it's a signal processing task, you know, it's, there's a lot of very simple algorithms that would do some kind of dynamic range compression, right?
Yes, because as you thought that the neural network is a black box.
Yeah.
This is something which is very nice because we see what is inside.
Exactly. That's
maybe if you will go this direction, then you will lose this property, and you will have again something which
I don't think it will become fully deterministic. I mean, you see the n-square connections.
If you combine this with this neural network approach, then you will lose this clarity what is happening inside.
Yeah, of course, but I'm not so interested in having a task solved. I'm more interested in developing our understanding of signal processing and you know, kind of working both ways. Because it's a bit of a boring Swiss knife in our field. You know, it's like, what do I want a great coffee? Well, a neural network will learn how to make your favorite coffee and kind of keeps closed doors. It's all behind the scenes. So that's the idea here.
I am in communication more in communication theory, error control coding, but 2 weeks ago I put in our system for students that I will also want that they make some experiments with these neural networks or data mining and to make some research if we can somehow optimize these networks.
All right, yeah, exactly.
And I don't know where it will lead, but it's interesting. That
yeah, I really hope. I mean, for me it was a big eureka. It was sometimes in the winter, not much activity around, and I was like, wait a minute, but I can actually connect the two domains. So without being too pretentious, I kind of think I've managed to find a connection between two fairly large domains, but there are so many details, engineering things, that it's not really my thing. I mean, I kind of graduated from a music academy.
Okay, congratulations. So, it's very interesting and very nice thing.
Yeah, well, we'll see. I mean, one of our major scientists in digital audio, Julius Smith, he's actually the father of physical modeling, pretty much. He said he found it very interesting. He said he saw some potential, and then some other guy said, well, no. So we'll see. I mean, I think it you know, the proof of the pudding, as they say in Britain, is in eating it. So far, it's just a proposal, and I was keen. I sort of have the imagination that this will be a way forward. So I just put it in stone. Here is my name. This is my thing, and I'm kind of a conceptual artist as well. So normally I would leave it at this stage. I would be like, oh, that's fine. That's just great. It looks good. Before I ruin it, you know, before I find something wrong with it, probably just leave it there. But as I said, the Mimic project is a very interesting new thing, which kind of tries to bring neural computation and also machine learning really close to the research community. I mean, most of digital audio experts are not really MATLAB wizards. Some of us are, I mean, some of them are, I kind of use it. But we have our other tools that are really handy and kind of quick. So now with the Mimic project, we actually have all this suddenly translated. And it's actually about 2-3 weeks that they've released it, so it's really fresh. So hopefully we'll see this develop.
Congratulations.
Thank you very much. Thank you very much for your attention, for your interest, and see you around.
Thank you.